before getting back into balls and air, obviously the second midterm, I've given back the papers. If you don't have them, they're in these literature racks along the second floor corridor. What to say about them? It was a little bit harder test than the first test, so the scores were a little lower. I had something worth saying that I don't remember anymore. The final exam is a double-length exam. That is, it's 60 questions, counts twice as much as a midterm. I view it as the third midterm, or half of it is the third midterm. The other half is sort of a comprehensive across the semester. So if you had trouble with this exam, you will see questions like it again in the final. Learn from the mistakes and hopefully do better. Any general questions about the exam things? I'll try to make videos, solutions, and put them up there in the near future. And okay. All right. So balls in air. Where I left off last time talking about balls in air before the exam, and my pointer, is the flow of air around a ball in sort of the perfect situation. And we'll see in a moment that this is a rare occurrence because of turbulence. So the story was this, that when air is flowing past a ball, and I hope that you're now comfortable with the idea of thinking of air going past the ball, even if you're playing a sport in which presumably the ball is moving through the air. It doesn't matter whether the ball moves through the air or the air moves past the ball. It's the relative motion that matters. So you can choose some frame of reference in which to watch this activity. And it makes sense to choose the one that's the easiest to think in. And watching a ball move through air is hard because you have to keep moving your attention. So let's not stand here with the air and watch the ball go by. Let's move with the ball and watch the air go by. Is that okay with everybody? Or questions about that idea? The whole idea of this relative motion is all that matters. So if we're here with the ball, watching the air move by it, heading toward the right in this story. And where I did talk about was that as the air encounters the front of the ball, and this applies not just to the ball, but to sort of any object that sort of presents a face to that oncoming air, including a car, and that's, I do have problem set 6 up there, which is about the aerodynamics of a car. The car is just a misshapen ball. Okay, so with windows, you can play games with the ball. You live inside the ball. Okay, so the air encounters the front. It has to bend away so as not to go through. And for it to bend away from the ball, it has to be pushed away from the ball by high pressure at the surface of the ball. So the pressure here at the front of the ball is above atmospheric pressure. We know why above atmospheric pressure specifically? It's because far from the ball, it is atmospheric pressure, and this pressure has to be able to push these air streams, these streamlines, away from the ball. So if you compare this pressure to atmospheric pressure, this pressure must be higher. So that's why it's, in reference to atmospheric pressure, it's above atmospheric pressure. If you triple all the pressure in the room, it's going to be above the triple all the pressure in the room. It's just this pressure is higher than the ambient pressure, whatever that is. Is it okay with everybody, or questions about that? Coincident with this high pressure here, which is indicated by the purple end of the spectrum, the violet end of the spectrum. In my pressure, again, is indicated by the rainbow spectrum, and the violet end is the high pressure. So this is high pressure. It's also low speed. The air here is slowing down. It's converting kinetic energy into pressure potential energy. And you can see that in these drawings by the streamlines spreading apart as the air, sort of each ball of air that's coming by flattens into a wide disk. It's slowing down and moseying through. So that air is actually very slow. In principle, right on center, the air comes to a stop. It's sort of a theoretical thing. But a bug sitting here on the front surface of the ball would notice, wow, the pressure here is kind of high, and the air isn't going very fast. The wind is slow. Ooh, this is interesting. All right, going around the sides of the ball, the air has to bend again, has to bend the other way now, toward the ball. it's accelerating toward the ball, and for air to accelerate, it needs a difference in pressure, as usual. Gravity sort of has no role in this. For any ball that's human size, the gravitational potential associated with going up or down is so insignificant that we can just neglect gravity for these airflows altogether. There's almost no gravitational potential energy difference between being on the top of the ball and the bottom of the ball. So we'll just set it aside. So the air goes around the outside surface. It's bending toward the surface. It's pushed there by a difference in pressure between atmospheric far from the ball, and this must be below atmospheric near the ball. So it's truly below atmospheric pressure there. You might think that you need like a vacuum cleaner or something to create pressure that's less than atmospheric. But you don't. You just need flows that do things like bend toward a surface. If the flow bends toward the surface and it's atmospheric pressure on the outside of the flow, the pressure at the surface is below atmospheric. Okay? So this is low pressure, and it's indicated by the red end of the spectrum, the rainbow spectrum. And coincident with that is that the streamlines are close together, which is an indication that the flow is necking down and squirting through extra fast. So the air has sped up in going here. And so following the theme of Bernoulli's equation, remember, Bernoulli's equation applies to steady state flow particularly well. If it's not steady state flow, life is a little complicated. But if it's steady state flow, the environment isn't moving, and we're with the ball right now. So the environment isn't moving. Everything's great. It's just a perfect venue for Bernoulli's equation. And what Bernoulli's equation says, that if you follow drops along a streamline, their total energy doesn't change. But their total energy is the sum of three parts. Gravity's one, but we'll set it aside. The ones that matter primarily are pressure potential energy and kinetic energy. So if you follow along the streamline, the total energy per drop of air is constant, but the pressure potential energy and the kinetic energy can be trading off. And that's what's happening here. The pressure potential energy, initially the air came in at atmospheric pressure and a certain speed. As it came in here, its speed dropped and its pressure potential energy increased. So its kinetic went down, its pressure went up. Here now, its pressure went down, its kinetic went up. They're just trading off. And that flow continues on, and at the back of the ball, it does a mysterious thing. It again has to bend away from the ball to leave the ball behind. And that means it's pushed away by high pressure at the surface of the ball. So bizarrely, there is a high pressure patch behind the ball in the flow I'm describing right now. The air is slow there, the pressure's high there. Thoughts, questions, anything? I'll keep asking, and hopefully somebody will have a question. Anyhow, this is all the good news, and very simple arrangement. The structure of the airflow is really quite simple. This is, of course, a two-dimensional slice through the flow. We're not seeing, I can't draw three dimensions. But the flow, the flow over the ball and the flow under the ball is the same as the flow toward us around the ball and behind the ball. It's symmetric all the way around the ball. The air goes around the ball and then closes on the backside. Okay? So that's the good news. Oh, one more piece with this is if you look at the forces exerted by pressure effects on the ball, they're zero. Why? Because if you go to a point on the ball like this one, and you look at the pressure there, and you go to the other side of the ball, oh, it's the same pressure. So it's completely symmetric all the way around the ball. Every point on this side has a corresponding point on the far side at which the pressure is the same. So it all cancels. There's no net pressure force on the ball. When the ball experiences gravity, what else does the ball experience? It experiences what's known as viscous drag, which is the drag associated with just the airflow going past its surface and rubbing. So the ball does experience a form of air resistance, known as viscous drag. It's not reflected in any of these streamlines because the streamline story, and I've drawn here, is done assuming no viscosity. If you add viscosity, it makes the system a little more complicated. It's not worth changing the drawing to reflect that. Furthermore, I'm not sure I know how to calculate it well, so I decided not to. But the ball does rub against the air rubs against the ball, and so the air leaving the ball isn't going quite as fast to the right as it was before it came to the ball. The ball actually does push the air opposite the air's motion. The air in turn pushes the ball opposite along the air's motion. They push on each other. From the perspective of the ball, it slows the air down a little bit. The air was coming by it at one speed, it leaves going a little slower. In real world situations where you're watching a ball move through air, the ball slows down a bit. It's accelerating backwards against its motion, and it's dragging the air along with it a little bit. So that's why it's called a viscous drag force. The ball drags the air a little bit. Okay? Where does this show up? Well, this kind of drag is always present in a ball moving through air. But that beautiful flow like that doesn't happen very often in air because of turbulence. You don't get this perfect laminar flow in any ball sport. You get turbulence, which I'll come to in a minute. In order to avoid the turbulence, you remember the battle between viscous effects and inertial effects? Viscous effects being the friend of order and laminar, inertia being the friend of chaos and turbulence. If you want to make the flow laminar, you have to give viscosity a chance. And you do that by just diminishing inertial effects to their just barest minimum. The problem is air's viscosity is so low that it's very hard for air to stay orderly in a flow. So you have to go very slowly with little obstacles. And with a normal ball, the beach ball, it's totally hopeless. It's a big obstacle. If it moves at any speed like this, it creates turbulence. So the context in which in air you see this kind of flow are particles, like dust particles. What you've seen dust floating wrong word of course, hovering around or seemingly in air when sunlight strikes it. And the dust pieces themselves are little bits of, they may be little bits of ash, droplets of oil or something like that, or pieces of organic matter, all of which are dense materials. They do experience a little buoyant force, of course, because they're displacing air, but they're way denser than the air. So if all they had to deal with was buoyancy, they would come down. They're like a rock. But they don't. They experience viscous drag. They're very slow moving, and they do have this beautiful flow around them. But even when they go as fast as a millimeter or a couple millimeters per second through the air, they experience enough viscous drag force that it's comparable to their weight. They're little guys. They're tiny little things. It's a general theme, and well, if you start with a ball like this, its surface is proportional to its radius squared. Remember these things from geometry way back? Radius squared is surface. The volume is radius cubed. So weight is proportional to radius cubed. You don't have to remember this. I'll do it anyway, though. The weight of something, if this were solid, would be proportional to its radius to the third power. Its surface, which is what it uses to experience viscous drag, is proportional to radius to the second power. You can give the surface effects more and more weight, more and more importance by shrinking the radius. As you do, the weight goes down. If you have the radius here, the weight goes down by a factor of 8, right? 2 to the third power. But the surface goes down by only a factor of 4, 2 to the second power. The point being that when you go to little things like dust particles, their weight is hugely diminished, whereas their surface is diminished a little less. They got more, the surface is getting more important compared to the weight. And the point then is that the little stuff, they present little obstacles, they have very little weight, so it only takes a little force to support them against the pull of gravity, for example. And so dust particles, in truly calm air, dust particles are descending slowly through the air, but they very quickly reach what's known as terminal velocity. So what's terminal velocity? It's something, you've heard terminal velocity forever. When something falls through air, all my discussion of falling balls, way back at the beginning of the semester, they all assume no air effects. Set aside the air effects. One of the air effects we know already is buoyancy. That certainly affects balls a little bit. If the ball is a very light, fluffy one like the beach ball, it's a more significant effect. If I filled the beach ball with helium, it would be a huge effect. Okay, so buoyancy is there, but also there's this air resistance effect. As the ball begins to pick up speed as it descends, it begins to experience more and more drag forces. Which types of drag force aren't immediately important, but you start getting an upward force as you move, as the ball experiences an upward drag force as it moves downward through the air. You okay with the direction of the force? Upward as it descends? You know air resistance, you're going along to the right, you get air resistance to the left. You go down, you get air resistance up. So that air resistance shows up. It turns out it increases with speed. We'll see how, the details don't matter at the moment, or maybe ever, but the faster you go through the air, the stronger those air resistance forces become. And that means that when you originally drop off some incredibly high platform, and you're looking at the little dish of water below, and you're doing one of these stunts, you're going to land in the dish of water and be safe and sound. And you're looked at, when you first step off, and you're not moving through the air yet, you accelerate downward to full acceleration due to gravity. But as you begin to pick up speed, the net force on you isn't entirely your weight. It's your weight plus this upward drag force. And that gets stronger as you go faster and faster, until finally the upward drag force is equal to your weight. You've got this blast of air coming at you, and that upward drag force is as strong as your weight, at which point you got your weight downward, this drag force upward that's equal in strength, they sum to zero. The net force on you is zero. As a result, you coast. And that's the experience of skydivers after the first few seconds out of the plane. During the first few seconds, life is complicated because they start moving, they step out of the plane with a big horizontal velocity, that of the plane. They do some complicated thing. And then after a couple of seconds, they're pretty much lost any horizontal component of velocity and momentum. They're just going down. And they're going so fast down that the air resistance force balances their weight. That incidentally, so they've hit what's called terminal velocity. Terminal velocity, it's the velocity part, it's always downward. It occurs when your downward speed is so high that the upward drag force balances your weight. Okay? For humans, and I'm afield from this story with the ball, but for humans it's about 100 to 200 miles an hour depending on how what your shape is. If you work to catch the air as much as possible, you go down flat like a pancake coming down, it's more like 100 miles an hour. If you pull yourself into some sort of dagger slicing through the air or some sort of tuck, you can get to 200 miles an hour. I think those are the rough figures. Some of you may have skydived before and know them better than I do. But you have some control over how fast you go. You okay with the idea of a terminal velocity? Anything falling has one, and they vary. For dust, it's a couple millimeters per second, depending on the size of the dust particle, maybe what it's made of and its shape. It's really, really slow. As a result, in truly calm air, the dust will gradually descend. It's moving down at its terminal velocity, and it will settle on the top surfaces of everything in the room. And you see this, right? You have a room that you've left closed for a week or a month, and you come in and there's dust on the top surfaces of everything. That's because in the calm air, there's been an opportunity for the dust to just work its way through the air, straight down until it lands. If the air isn't calm, it's blowing around, the dust is still trying to go through the air at its terminal velocity, but if the air is rising, it's the relative motion that matters. If the air is going up at a meter, let's pick a number, 100 millimeters per second, and the dust is working its way through at 3 millimeters per second, the dust is going to be going upward. It's just not, it's on an up, it's descending within an upward elevator, the air, that being the air. So next time you see dust motes floating in the air, floating, again, wrong word, in the sunlight, you can sort of watch the dust particles. They're trying to come down. They're having a tough time of it because the air is moving off it. You okay with this? Or questions again? Keep asking questions. All right. So that's life for the littlest things moving very slowly. They experience this beautiful laminar flow around them. They consequently experience only viscous drag. In the real world, however, for balls and stuff, I won't do this one. Let me just go. Do I want to do this one? Yeah, I'll do this one. When a car drives down a street full of fallen leaves, the leaves swirl around behind the car. You know, it's that time of year, this is what you see. What kind of flow is present behind the car? How many think it's turbulent flow? Fine. How many think it's laminar flow? Yeah, no, it's turbulent flow. And what you're seeing is the leaves being pulled along by these drag forces, but they're not viscous drag forces anymore. They're another type of drag force associated with that turbulence itself. So the flow for any object, whether it's a ball, whether it's a car, moving at reasonable speeds, it's going too fast through the air, which is equivalent to the air is going too fast by the ball or the vehicle to stay laminar. It shreds into turbulence somewhere along its passage past the ball or the car. And once that happens, it's a big swirling wake that typically has a pressure of about ordinary atmospheric pressure. The big highs and lows and pressure that you get with laminar flow are pretty much wiped out by the turbulence. Yeah. So this slide is going into the gory detail of why you get turbulence behind an object like a ball. The simplistic way of doing it is just simply to look at Reynolds number. Remember Reynolds number, which is a dimensionless, that is, it has no units. Dimensional is a number. It's just a number that compares inertial effects divided by viscous effects. Who wins? And if the inertial effects get strong enough, you get turbulence. So if you go fast enough, you should get turbulence. What triggers the turbulence? So the fact that you can get turbulence at high Reynolds numbers doesn't say why the turbulence starts. And this is the story of why it starts. And this is the wordy story. Maybe I'm looking for a prop, so this will do. So if you remember the ball with the air flowing past it, so here comes the air. The air encounters the front of the ball and spreads out, bends away from the ball, high pressure, so forth. It goes around the sides, low pressure. It's bending toward the ball, low pressure, high speed. This air now is at low pressure, heading forward, sort of generically forward. Whether it's what exact direction we'll worry about in a minute, but it's at low pressure. And when it finishes its trip behind the ball, it's going to be at high pressure, right? Because that's the bend away at the back. That's a peculiar situation. You've got fast-moving but low-pressure air here trying to go to the back of the ball where it's slow-moving, high pressure. It's air flowing into a rising pressure. And I've said it for a week now or something like that air loves to accelerate in the direction from high pressure to low pressure. I mean, it does, right? You give it an opportunity, where there's high pressure here, low pressure there, it's going to accelerate toward the low pressure. So if you've got low pressure on the side of the ball and high pressure behind the ball, the air is going to accelerate towards the low pressure on the side of the ball. And it does. The air going around the back of the ball is slowing down. It's flowing toward the back of the ball, but it's being pushed against its velocity by this pressure imbalance. So it's slowing down and its pressure is rising. The jargon name for this flow from low pressure to high pressure, it's called an adverse pressure gradient, for better or worse. But I want to make sure that with the name, I don't care whether you have any connect to it at all. But the idea that it is a flow going into higher pressure, that you should understand. Are you okay with that idea? That's potential problems, because for the main airflow, it can do it. It can go from low pressure to high pressure. It is slowing down, but it manages to keep moving forward and get away from the ball. According to Bernoulli's equation, life should be good. It should get away from the ball. It has enough energy to do the job. But the flow of air near the surface is in trouble, because in addition to the world of Bernoulli's equation, it has to deal with the fact that it is actually rubbing on the ball's surface. So there is a layer of air very near the surface that has an additional complication. It's aware of the surface, and it's aware that the surface is sucking energy out of it because of viscous effects. That layer that knows the surface is there, the flow out here doesn't know the ball is there, let alone the surface. It's too far away. But the layer of air really near the surface, it knows. It's like there's air near that ball surface that's stopped. Oh my gosh, this is hard work. And that layer that's aware of the surface has got a name. It's called the boundary layer. The air flows of everything there's the main flow, and then there's the flow that's aware of the environment it's going through. And the flow that's aware of the environment, the motionless environment, is known as the boundary layer. It depends on the context how thick that is. The winds, you go 500 feet up, and they have no idea. The wind up there isn't aware there's a ground here. But the wind a few feet up is very aware there's a ground here. It's rubbing. It's experiencing problems. And so there's a boundary layer here near the surface of the Earth that interacts with the ground. For a ball, it's a very thin layer, maybe a few millimeters. But the air in that layer, going from low pressure to high pressure, has this extra problem that it's losing energy to heat as it rubs. And that air tries to go to the back. It's being pushed against its velocity, so it's slowing down, rubbing, it comes to a stop. It just plain runs out of energy. And instead of getting to the end and leaving, we made it. It gets partway, it doesn't make it. It comes to a stop. And when that happens, it spoils the whole concept of steady state flow. You can't have the air continuously flowing in and piling up here. It always stops there. You have more and more and more air as the seconds pass. So it doesn't happen. Instead, what happens is the air comes to a stop there. It spoils the steady state flow. It creates kind of a wedge of air that pries the whole main flow off the ball. And so what leaves behind the ball isn't this beautiful flow to high pressure and then leave. It's work its way from low pressure to turbulent wave, and there's just a big wedge of crud behind the ball. And the name for this effect it's the triggering effect is called stalling, because the airflow that was trying to go to the back of the ball very near the surface, that is in the boundary layer, stalled, came to a stop, and pried the rest of the flow off the back of the ball. And what's behind the ball then is a turbulent mush. And I don't even know how to draw it very well. And this is about the best I've ever managed to do it. The books, to learn how this stuff works properly, you can't go to physics textbooks, because the physicists aren't all that good in the world of fluids, except for the specialists. You have to go to the aerodynamics people. Yeah. the air is trying to leave the ball behind and go on at full speed, neglecting viscous drag forces. In this case, the air that ends up in that turbulent wake is pretty much moving at the ball speed. Its pressure is pretty much atmospheric, and it is now moving at the ball speed, which in this drawing is motionless. So the air comes along here and it's motionless, so it should never leave. From the perspective of the ball, so this is equivalent to the ball going this way through calm air. This ball right now is taking the air that was coming at it and bringing it to rest in its frame of reference. It is dragging this whole, there's a whole, if I start far enough back, there is a whole column of air moving along with the ball. If I put paint in it, you'd see here it is swirling around, but moving with the ball now. So the ball is dragging the air along with it. And if you go into that region, that swirling air pocket, you walk behind the ball in this, like me. The wind is not at my face anymore. I'm walking in pretty much motionless but somewhat swirling air. And that's the whole concept of drafting, which shows up in a lot of sports. If you want an easy trip through the air in some sport where you're moving forward, whether you're running or bicycling or swimming or whatever, go into someone else's turbulent wake, because that air is being dragged along by the person. They have already transferred their precious momentum into the air, and it's going with them now. And when you get into it, it's sort of motionless with you. And it doesn't push on you very much. Is that okay? Other questions? So the swirling air pocket, good news and bad news depending on the context. It's a real problem for a ball trying to make its way through air, because the ball will develop this turbulent air pocket behind it, and that leads to a very strong drag force. I should point out where the drag force comes from. Because it's not a viscous issue anymore. It's pure pressure. The pressure, remember the pressure way back when, the pressure kept canceling between one side of the ball and the other. You could add up all the pressure effects and they were zero. They're not zero anymore. Here you got the high pressure in the front of the ball, but it's missing its balancing high pressure behind the ball. So there's a net backwards push on the ball due to a pressure imbalance. And you can experience this very easily. You probably have. I sure have. When you're driving along as the passenger in the car, to avoid liability, don't do it as a driver. Eyes on the road. Okay. When you're a passenger, you put your hand out the window. If you ever open the things anymore, given the air conditioning, you put your hand out. You're at 60 miles an hour. Whoo, there's a tremendous pushback on your hand. And that pushback is the high pressure on the front. Your hand is playing ball. High pressure on the front, the air goes around the sides where it's low pressure, but it's balanced pretty nicely so you don't feel any up or down effects. And then in the back, big air pocket. Atmospheric pressure, turbulent wake behind your hand. So there's high pressure in front, nothing behind, nothing important behind. You get pushed backwards. I hope you've all had experiences like that. You sort of, in your memory, remember those experiences. Incidentally, if you do start tipping your hand funny, you get these up and down forces. Those are lift forces. Those are going to fly planes. And they have to do with the high and low pressures, the pressures that you get on the sides of the ball. Okay? All right, so this is called pressure drag. It involves, in its simplest form, it involves dragging a column of air behind the obstacle, whether it's a ball, whether it's your hand, a car, that's pretty much got the cross-section of the obstacle, plus or minus small influences. So this ball moving through the air leaves behind it a turbulent wake that's a column almost as big as the ball. Just pulling that column of air along with it. If it's air, that's a problem. If it's water, it's a really big problem because you're dragging this massive, dense stuff with you. And this is why it's hard to go at high speed through water if you drag a big water pocket with you. It's nasty. Okay? This force, this pressure drag force, incidentally, goes as as the square of your speed. Why? So if you double your speed, you get 4 times the force. The reason for that is, because if you think you're dragging this column of air behind you, if you go twice as fast, first off, you encounter twice as much air every second. That column is increasing in length by twice as much length every second. So that's one factor of your speed. Double your speed, you double the column and the mass therein. The second thing is, as you double your speed, you're dragging the column along at twice its original speed. You have sped it up more. So the force you need to bring it up to speed doubles. So you're dragging twice as much air, and you're having to bring it up to twice the speed. That's 2 twices. It involves twice as much momentum transfer every second into that air. And with that comes 4 times, maybe I said that wrong. As you double your speed, you are transferring 4 times as much momentum into air as you did at original speed. Twice as much air mass, twice as much final speed in the air mass. So that involves an impulse and involves a force that's 4 times as big. The point of this is just explaining why the faster you go, the worse this effect, the slowing effect of air drag becomes, and it goes not just as your speed, it goes as your speed squared. So driving a car at 60 miles an hour versus 30, the car is dealing with 4 times as much air resistance. Swimming, double your speed, you're dealing with 4 times as much water resistance, and so on. Boats. This is why boats, by and large, the ones that actually immerse themselves in the water and don't skim the surface, the ones that immerse themselves in the water, they're often dealing with, as they go up in speed, this speed squared effect. It's very hard to make a boat move through water at faster than 100 miles an hour. Just would take tremendous forward push, and therefore a huge amount of work to get the boat moving that fast. Okay? So what are you going to do? If most sports have to live with that pressure drag problem, and it's a serious influence on a lot of sports. It means that the book section concentrates a lot on baseball. For a pitcher throwing a fastball towards home plate, it may leave the pitcher's hand at 100 miles an hour, but it's facing this tremendous drag force because it's going so fast. And it's pulling this whole column of air forward at 100 miles an hour. It slows down to something like 80 or so by the time it gets across this home plate. Don't quote me on that number. I'm rusty on the exact numbers of how much it slows down. But it's a big drop between the pitch and the arrival at home plate. All the other sports, soccer, volleyball, these are balls that are hollow. They don't carry a lot of momentum with them. They really can't afford to lose a lot of momentum to the air by pushing through it. Okay, so the game of golf is one that's sort of particularly interesting because, well, actually, there are 2 parts to this. Golf artificially, with the dimples, artificially creates an effect that I should say also can come, and I should introduce first, also can come from going especially fast. It turns out, let me do this. Do it with this drawing. Or I could do it with a ball too. So what I've described up to this point is if the airflow fails to flow properly from the sides of the ball where the pressure's low to the back of the ball where the pressure's high, it peels off and creates this terrible turbulent wake that's almost the size of the ball in cross-section. For a car, it's almost the size of a car. It depends a little bit on the shape of the ball or the car or the truck. And many vehicles these days try to shrink the cross-section of the wake they leave behind them. A moving box is not the ideal shape to drag through the air. So a lot of delivery vans and stuff like that with a box profile, they leave a turbulent wake that's pretty much a box-shaped column chasing the car. But if you taper it, you put on various airflow control systems, you can make that column smaller. And so if you watch, like one of the most common ones of these is trucks, the semi-trailers, the cab and the trailer. The cab will have a aerodynamic piece that connects it with the semi-trailer, so that it's trying to minimize. This ultimately minimizes the turbulent wake that's left behind the entire vehicle. High-speed trains are very streamlined. I mean, just in general, the idea of a streamline, another word you've probably heard your whole life. It's trying to preserve the streamlines. Turbulence, no streamlines. Laminar flow, streamlines. Cut the thing that's trying to drill through the air, cut it such that it enables the streamlines to stay intact as far as possible. Okay, back to the business of balls going through air. I've described the problem of the turbulent wake. It turns out, oddly, that if the ball moves especially fast through the air, or the air moves especially fast past the ball, something strange happens in the thin layer of air near the surface, what I call the boundary layer, what everybody calls the boundary layer. The air in that boundary layer, if you recall, is the source of trouble. It slows down in trying to go into this rising pressure, and it comes to a stop. If you can give it help, get it farther on the back of the ball before it slows down significantly, it's possible to keep the turbulent wake from developing early on the ball. You can delay its creation and even the wedge effect so that it forms closer to the back of the ball. How do you help that boundary layer go through? The way that you can help the boundary layer through is by making it tumble locally. A little bit of turbulence in that layer itself, not in the main flow, just in that layer where it's on the surface. It is very aware of the surface. It's having battles between inertia and viscosity there, and so it can begin to tumble. And when that happens, you get what I think of as a tag team effect in the layer. The layer has multiple streams in it. You can sort of divide up into threads, moving their way around the back of the ball. And if you allow the threads to interchange, so that the thread that's right closest to the surface of the ball doesn't stay there forever. It plays tag team with another thread of air. You let them exchange. They can take turns doing the work of struggling to the back of the ball, and they make it farther into the ball before they run out of energy and stop. You're sharing the burden. And in this case, prompted by the very high-speed flow, you can get the boundary layer to go farther in the back of the ball before it comes to a stop and be more resistant to the wedge effect coming back and prying the flow off the ball. And the result of all this is that you get a smaller wake. I mean, so the bottom line, you can treat this as blah, 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 smaller wake. You leave a thinner column of air behind the ball. So this occurs when a ball moves very fast through the air. It needs a very high Reynolds number, something like 100,000, which is just technical details. But you get a smaller wake. And this occurs in each sport at a certain speed. Above a certain speed, you get that turbulent boundary layer and you get a better flow behind the ball. For baseball, it's about 100 miles an hour, my understanding. So a ball is traveling above about 100 miles an hour has a smaller wake behind it because it has this funny behavior in the boundary layer that helps shrink the wake. Okay? And the result is the ball experiences less pressure drag than it would if it had the full-size turbulent wake, and it flies better. And the reason this, I guess, is important in baseball is that nobody can throw the ball fast enough to get this smaller wake. They're all thrown balls always have to deal with the big wake, but a batted ball can go fast enough to get the turbulent wake and go farther as a result. With less drag, it just simply can keep moving at top speed longer and travel farther. Okay? In other sports, they may or may not be able to get into this regime where they get the small wake. But a golf is a case where nobody waits around to get to that speed. Instead, they deliberately create the turbulent boundary layer that creates the smaller size wake behind. You okay with the concept of a turbulent wake? It is the wake that you see behind boats often, some of the wake that you see behind boats, but even in the air, there's a wake there, this patch of disturbed air. Anyhow, the purpose of the golf ball dimples is that the ball travels better. So I can show you, these are my document camera. These are 19th century golf balls. When they first started making golf balls out of essentially plastics and rubbers, they didn't at that point really know they did not understand what plastics and rubbers were, but they could make them, and are very primitive ones. They would just mold a nice smooth ball. Looks great, should be wonderful. Didn't fly very well. When you hit it, a 75-yard hit with a golf club was about all you could ever expect to get. And people discovered that the more you use the same ball and beat it up, the better it flew. Because all the dings and bumps and trouble you create in the surface has the effect of tripping the boundary layer. Like tripwires, like you start to tumble. They cause that little boundary layer, the part that's aware of the surface, to begin to tumble, and that gives that tag team effect. It allows the flow to stay attached to the back of the ball longer and creates the little wake. So rather than waiting for the ball to get beat up, people started beating up the ball deliberately. So they would go after it with a chisel and mess up its surface, and you'd make a better ball. It would fly, instead of going 75 yards, now it would go 200 yards or something like that. Eventually they got into molding stuff. Initially there were bumps on the surface. So it's bramble, it's like a brambleberry. And then of course the dimples that are the modern tool for tripping the boundary layer. But that's the point of the dimples, is to trip the boundary layer, to allow different parts of it to take turns struggling to the back of the ball and the rising pressure, and you get less drag as a result. I had hoped that tennis balls would be exhibiting the same effect, and I'm not alone. People studied it finally. So some people people did research on tennis balls to see whether the fuzz has this effect. The fuzz it surely has two different effects. One is it increases the viscous drag effects because it like catches the air. And the other is that it trips the boundary layer and potentially creates a small wake. You know, which one wins? It turns out that the dominant effect is increased drag because you got this fuzz out there catching the air. And the way people figure this out is by doing things like shaving the tennis ball with an electric razor, getting it wet. Anyhow, the golf ball seems to be sort of unique in having this deliberate trip the boundary layer effect. That leaves, and I'll just have to leave for now. The last detail that I'll just tell you in advance is curveballs, which show up in all the sports as well, whether it's baseball or volleyball or soccer. I don't know whether you know the Bend 'em like Beckham movie, which is a little before your time, but it's probably still around. Anyhow, we'll do curveballs, which involve lift forces, on Friday.